Hello everybody and welcome to this tutorial. Today we will create an effect made with Krakatoa and TyFlow to make this sphere, and we will also add some particle occlusion on it. And this is also a very difficult thing, especially at my previous project and also on the Audible commercial that I worked on as well. The main benefit of particle occlusion is that you achieve a very realistic look, as it avoids the backface particles, so you get the idea of solid objects if you want to present effects on objects or on geometry shapes. So let's start. Okay, first of all we go to customize unit setup, and then we change the units into meters under system unit setup. Alright, press Alt and W, so we get this full frame view, and then we will create a sphere. Okay, let's say we create a sphere with a radius of 12. Okay, first we will create a sphere, and yeah, I would say we give it a radius of about 30. And we make the resolution up to 100 segments and place it at the coordinate 0, 0, 30. Yeah. Next we will create another sphere, and this will be much smaller. I would say we will give it a radius of 8. Move it up. Yeah, something about here, or maybe just on the coordinate of 60 at the z-axis. Yeah, and maybe we will give it a little offset on the x direction, and this would be, let's say, 10. Yeah, just mark both of these spheres, and let's create another layer, and we will call it Geo. Also create another layer and call it Particles. And then we will create our TyFlow. TyFlow has also a free version. I will put the link into the description, and let's open the editor of the TyFlow object and create our particle simulation. First off, we will use the birth intersections operator, and that's why I decided to create two spheres. So leave everything as it is by default, except the end frame for the creation of the particles. Just change it to 0, and then at the Objects A tab, pick both spheres. Okay, let's see if there's something that we can recognize. You can disable the Geo layer, so we can see any changes or any particles coming up from TyFlow, but there's nothing in it. So we have to change the threshold of the intersection area. Let's say 9, and there's 2 little dots. Okay, let's change it down to 6. Yeah, that's pretty good. Alright, as you can see, the birth intersection operator creates particles at areas where 2 geometries are intersecting. Alright, another thing that would be very important for later would be to add a mapping operator to give the particles the texture coordinates of the small sphere. Okay, now what I want to do is make the particles go around the sphere in a vortex behavior, go down just until the ground and put some lines on it. So we have something like spirals, and that would be very cool, and those spirals will create some dust or emit some particles out of it. So first of all we will set the movement of the particles, and this would be done with a script operator. Yeah, we go through it very easily. Just remove the commented lines. Also delete that, and so on. And then we start creating some vectors. First of all, we need 2 vectors to get a vortex. So we need a vector that's pointing outwards, the z-axis of the first sphere, and another vector that is pointing downwards. Create point 3 and call it P for pointing outwards. This will be a new vector created by the components of the position of a particle, point X, and the next component would be the Y component, and the next will be 0 because we don't want the vector to point upwards or downwards. We just want it to point away from the z-axis. Also very important is we need each vector to be on the same length, a length of 1, so it will be normalized. So apply the method point normalized on it at the end. The other vector that is pointing downwards will be called downwards. It only has the components of 0, 0, and -1, of course. And we don't need to normalize this because it's of the length of 1. Now we can create our vortex. And this is point 3 cross method, outwards vector, and the downwards vector to get our cross vector. Okay, and last but not least, we only want a little tiny turbulence on it. So let's create a turbulence and give it the function of get call noise. And its arguments are time, which will be just t by the time that is currently in the timeline, the method which is giving us the current position of a particle, the frequency, which will be a low value. I decided for a value of 0.1, a scale value of 0.25, and a phase of 0. Okay, and this will result in our velocity vector. And this is a sum of the vortex, the downwards, and the turbulence. But the turbulence shall be a bit weaker than the other vectors. And last but not least, we will apply this velocity by the function setVel or setVelocity to our particles. At the very end, we will multiply it by a value of 0.5, floating, of course. Check if everything's alright. Okay, I misspelled the word velocity and I didn't see it. Okay. Okay, now that's all done. Let's check for the particles. Okay. And this looks good, but I will expand the timeline up to, I would say, 300 frames. Yeah. Okay, next I need to apply two things. First will be the object bind operator, because I want the particles to stick to the surface. So let's pick the object to bind on, choose lock to surface, and for the friction set a value of 0% because I only want them to stick to the surface but not on a specific spot on the surface. Okay, that's already very good. I will choose the display mode for large dots, and yeah. Okay, next thing would be to choose a property test operator, and this will check the position Z, and if they are very low at the floor, like if they have a position Z value of 0.5 and timing is on continuous, then the particles will be deleted. Okay, let's check it out. I will expand the timeline once more up to 400 frames, and now we should see how each particle will be disappeared at the end, and that's correct. Alright, we are done with the main particles, and let's go over to the spreaded particles. There are two kinds of spawned particles we want to get. Okay, the first particles will be the particles which are creating the line of the movement. Therefore, we choose the spawn operator, but we change the spawn mode from per step to by travel distance. Here we choose a value of 0.2, and we don't inherit any properties like velocity, so they will stick onto the surface and then will die after 30 frames. So go to timing on the delete operator, switch over to event age and choose 30. And let's have a look at it. Nope. Oh, and of course we also have to change here from on event entry in the timing section to continuous. Okay, let's have a look at it. Okay, that's very nice. And they all disappear until frame 400. Yeah. Okay, and now it would be time to create the second kind of particles. Also with the spawn operator. And of course also we change here to continuous in the timing section. And also we change to by travel distance and maybe give them a value of 0.1. And this time we will give them an inherited velocity, but only by a value of 40%. Give them a divergence of 75 and let them die after 60 frames. So we also have another event to connect. And also, if they have inherited velocity, we still want them to slow down, so we give them a slow operator and maybe give them a slowing percentage value of 3, I would say. And also they need to stick to the surface, so just press Shift and drag this operator here, so we will copy it. Yeah, and that's it. Let's check it out. Okay, that's very good. I would say in the end I will increase the threshold value in the birth intersections operator just to get more particles at the beginning, so we also have more lines and more spreaded particles across the sphere, just to get a bigger impression of the particles or the surface of this sphere. And yeah, but before I will convert the simulation to Krakatoa particles, I will also give them material IDs, just to be able to separate the particles later in Krakatoa magma modifier. So in this material ID operator, I choose a value of 1 for the first particles, which will be the tips of the trails, and the particles which will be forming the trails have a value of 2, and the particles which will be performing the spreaded particles across the surface will have a material ID of 3, so I can separate them perfectly and give them different emission values later. So now it's time to export the particles. Choose the export particles operator, take the PRT format, and also change the H channel, but the H channel is unactivated by default. Go to the cache tab and enable H. Okay, then we also want to export the texture coordinates that we get from this operator and the material IDs. Alright, and that's it. I decide to change the threshold down to a value of 3, so we get more particles. Yeah, you see, there are much more lines or much more particles that are forming lines, so we get even more particles in total for our effect. Alright, I will just export the simulation and then we move over to Krakatoa magma modifier. Okay, we are done. Export is over. Okay, let's disable the flow. Go to the Krakatoa tab and choose the Create PRT Loader. Press Shift. Okay, and let's pick the particle files. Choose No because we didn't make any partitions, but if you did, choose Yes and pick the partitions. So you have a much higher particle count for your effect. I also choose every nth particle and choose 10% to be displayed in the viewport. And this is very nice, but they are all looking the same. So first we will give them a color, and that would be a bit dark, maybe a dark blue, something like this. Okay, also we need to create a light, and I will choose the default layer and create the light, so it will be placed in the default layer. And I choose a very simple Omni light in the standard tab, and the lights of 3ds Max. Yep, and let's take a first look at it. Somewhere in between, maybe here. Let's choose iterative rendering mode, and also, yeah, of course, choose HD. Okay, it doesn't look any kind of satisfying, so we enable absorption and go down to a light pass value of 1 and -2. Okay, that's already a little bit better, but now we start with the emission behavior. Okay, let's go to the Krakatoa PRT Loader and choose in the modifier tab a magma modifier. Choose an input channel and take the texture coordinates. Best would be if you take show existing channels only, so there you get it. Press C, choose breakout, take the X value, choose function blend, yeah, put it into the blend amount, and then add 2 input values of the type of vector. Then take a color, bright color between green and yellow. There's the other color. Take something here. System, elbow, so we can take from here 2 different output nodes. The first will be emission, and the second one will be PRT, viewport, color. So we see everything that goes into the emission channel, also in the viewport. Alright. Let's open the render window, enable emission, and let's see what we get. Okay, that looks very nice so far, but I would like to go a bit further. Okay, first I would say let's multiply the color by the magnitude of the velocity. Input channel velocity, vector magnitude, multiply by maybe 0.5, and also multiply it by the age of the particle. And as you have seen, the particles will reach maximum age of frame 60, which will result in a value of 2, as the age channel doesn't represent the frames since the birth of a particle, but the frames divided by the frame rate. And the frame rate here is, as by default, NTSC, so 60 frames by frame rate of 30 would represent 2 seconds, so the maximum value would be 2. So we will divide our age channel by 2, so we get a range of values between 0 and 1. Press A for the arithmetic section and choose subtract operator. Put our division in the second input socket, so we will get values from 1 to 0, counting down over a lifetime of the particles. And this will be multiplied with the other multiplied value, which will be the speed of the particle. So fast and young particles will be the brightest, and old particles will be dark. Okay, let's multiply it. And let's take a look. Okay, that's very nice, I think. But we don't see the trails. Get back into the magma flow and give the trails another emission behavior. I would give them also a behavior over lifetime, but they should diminish a bit faster. So I will multiply the H channel by a value of 1.5. And because they will die 30 frames after their birth, they will have a maximum value of 1 in their H channel. But now that I multiplied the H channel by 1.5, they will reach the value of 1 even further. So subtract, same as here. But then afterwards, to avoid negative values, connect the line with the function section and choose the clamp operator. Also, because we have values between 0 and 1, we can interpolate them, so they diminish a bit faster, but they still be very bright at the beginning. So choose in the arithmetic section the power operator to give it a power by the factor of 2. And now we will multiply this ramp over lifetime, or this interpolated ramp over lifetime, with an input vector, and this vector will be bright blue here, and maybe in the end we will brighten it a little bit up, maybe by a factor of 3, connected with the viewport color. Yeah, that's pretty good. So, but now it's not shrinked to the trails. So we take advantage of the material ID channel to distinguish the particles. And we do that by press I, channel, material index, draw a line, choose the logic section and choose the max operator. Okay, the line is completely wrong. This will be our selector. Increase the number of inputs to 4. For some reason it counts the selector input socket width. But yeah, now that's the correct number because we have 3 different values in the material index. So in the case of 0, which will be the tip particles, we only get, I would say, very bright single particles, very bright white single particles, and with very bright I mean, let's multiply it by 50. Okay, and don't worry about the material ID numbers here. In the channel itself, the values will be iterated up from 0, like in each programming language. Okay, so our particles on the line, which are here in event 3, they had the value of 2. So if the material index channel has a value of 1, the particles will get the emission values from here. And in the other case, which are the spread particles, they will get this color that we created first. Let's connect this here into the elbow, just because I like the look of it. Alright. Let's press update and see. Yeah. Okay, that's very nice, I think. You can see the trails a little bit. Okay, I go a little bit closer with the camera. Yeah, I think that's good by now. I mean, you can redo the whole simulation with more partitions, for example, or you could also decrease the travel distance, like here, just to get more particles in one line, because yeah, you can see some little gaps in between. So if you increase the step size, yeah, it will be more clear. But that's okay, because I have plans to get a very nice depth of field view from Krakatoa, and we can achieve this by adding a camera onto it. And before we do that, I will create a circle, also here in the default layer. Go here, splines, circle, something about here, I would say, with a radius of, let's say, 120. Yeah, put it right here in the middle, move it up a little bit, and increase the interpolation steps up to 100. Okay, because now we want to add a camera. The target will be also in the center of the sphere. Give the camera target the same position as the sphere. Okay, and the camera itself will be placed onto this circle. Go to the animation tab in 3ds Max, constraints, and path constraint. Then choose the circle. Yeah, I would change this animation. So we get here in the motions tab, as you see. Change the first keyframe up to 50 and go to the last frame, because it always sets an automatic keyframe at the end of the timeline. And yeah, I would say we will decrease this value down, keyframes of course, to I would say 75. Okay. Now let's take a look into the camera perspective. Okay, the circle should be a bit bigger by its radius. Something like here. Okay, let's go back to the camera. Give it a Krakatoa camera modifier. Go back to the perspective view. And change this, the focal length, because we want to override it. Yeah, put it somewhere here, right at the closest point of the sphere. Check, of course, the override focal depth. In the depth field f-stop value, I would say put a value of 0.2. Go back into your camera, open the rendering window, enable this DOF bottom, decrease the quality up to 3, I would say, and let's check it out. Okay, not good enough. I would decrease the f-stop of the camera down to 0.05. Yeah, let's take a look again. Still not close enough. Okay, that's good. Now, yeah, I choose very low values as I like it the most. Yeah, and I think this looks very cool. Also, at the end we will render it with motion blur, so the single dots will be not so visible like they are right now. You can also play around here, decrease the lighting pass. No, that's not so good, or maybe something like 5, and so on and so on. Now we go over to the occlusions, because currently the particles are also shown from the back face, which would be hidden to the camera by the sphere itself. How do we do that? Okay, first of all, we will create another Krakatoa magma modifier, just to keep it a bit more simple. And then we will add with I an input geometry. Choose in the scene sphere 0 an input object, and here you choose your camera. draw a line into empty space, so the property query operator will appear. So we get the position of the camera, put it into an subtract operator, and here subtract from the position of the camera the position from the particles itself. So here, input channel position. Also very important, press V, normalize, because later we also want to apply the operator for vector dot product, just to check if the particles are visible to the camera or not. Because we orientate on the input geometry on the sphere. So first we will draw a line from the sphere and choose the nearest point operator. As the lookup point, of course, we take the position of a particle, so we get the information for a nearest point on the surface of the geometry according from the position of the particle. Click onto this operator and then we get the option of add face gray. Okay, all these lines are connected automatically, so we get information of the face where the nearest point seen from the particle itself is placed on. So in the drop-down list here, check out for the normal. And then we check the vector, which is pointing from the camera towards the particle, and check if the particle will look into the camera, if it would orientate on the normal of its closest geometry's face. And we do that by going to the vector section and use the vector dot. So we take the normal and get a vector dot product. So the vector dot and the vector dot operator always gives us values between a range of -1 and 1. -1 means that the vectors are pointing into the same direction, and 1 would mean if they are pointing towards each other. If we look at the sphere, all the normals from these faces are pointing somehow close to the camera or just a little tiny bit to the left or to the right besides the camera, and all the back face particles would rather point in the same direction of the camera, especially here in the center at the back side. So that would mean that all the particles right here at the side, which would mean in the range between -1 and 1, would result just in the middle, like with the value of 0. They would just be accepted by the camera and not be hidden by back faces. So we use a logical operator, less 0, so that all the particles with a vector dot seen from the closest point on the surface below 0 fit into a selection, like in the selection channel, and everything which is in the selection channel will be deleted by a Krakatoa delete modifier. Okay, let's check it out. Alright, now we only see frontside particles, seen from the camera, of course, because if I leave the camera and I disable the geometry, there are no backface particles right now. Alright. Let's go back into the camera. I think this looks very nice, and to perceive some kind of movement of the camera, I would create a plane here in the center of the scene and give it very huge dimensions, something like 500 by length and 500 by width. Go to the Krakatoa tab and choose Create PRT Surface. Alright, change this because we only want some few particles just to perceive the movement of the camera, because they are not moving, they are just there on the ground. Of course, they should emit some light. Go here into the Krakatoa magma flow, input vector by value of 1/1, so it is white. Multiply it, I would say with a random value, so position, go to vector, component sum, so we get an individual value here by each particle, because in Krakatoa surface objects we don't have particle IDs. Press convert to int, because now our function uniform random operator only accepts integer values as a seed. Let's change this up to 0 and 100. Multiply it by the white value. Return it into the emission output. Alright, let's see. Okay, that's a little bit too much. But in this case, I would say go to the Krakatoa settings. Here, scroll down to ambient PME, and this would result into darkening particles when they are further away from the camera. Like here from a distance of 500, and choose a color, something very dark gray, something like this. Yeah, go to the render window and activate this function here, where we see the gradient. Okay, let's look again. Okay, that's much better. Okay, now as the last thing I would enable the motion blur, adaptive motion blur, which always orientates on the maximum velocity value. Use the jittered mode. Okay, and let's take a look. Maybe add another frame. I'm still not so happy with it, but I guess that's only a question of the depth of field. So we'll go out of this once more, of this camera view. Select the camera. Now I would change the focal depth up to the middle or maybe the back of this sphere. So I will give it a value of about 200. Okay. Yeah. Let's check it out once again before we render. Okay, I guess I'm fine with it. But the very last thing would be change the color of the PRT surface for the plane to black. So there will be no color absorption from the light, and only particles will be seen with their own light emission. Alright, I will render this out, and yeah, I would say thanks for watching. If you have any questions on Krakatoa or any ideas for other tutorials, let me know. I will read each comment, and I'm planning to make more often any tutorials, so yeah, I'm thankful for each idea and question, and yeah, see you next time. Bye bye.